I'm here, and I thank you, Ron and CLL, for inviting me to do this, and I'm glad to see you people come here. And yes, there will be no math. There isn't any math in the book which I wrote, and I'll tell you about that. And there won't be any math here. The story started in 1956. As a physics student, I found myself at Harvard University, and the timing couldn't have been better. You know, the secret of life, it's all in the timing. And this was one of the very lucky breaks in my life. I had no idea, I hadn't heard of Schwinger at the time. But as I arrived there, Julian Schwinger, one of the greatest physicists of the century, had just completed formulating quantum field theory into its final perfect form and was beginning to give a 3-year cycle of courses that I'd caught just at the beginning of the course. I looked him up on Wikipedia, and I included this quote just to show you that I'm not just talking through my hat. He's recognized as one of the greatest physicists of the century. He's responsible for much of modern quantum field theory, the equations of motion for quantum fields. So I sat there for 3 years, took notes as well as I could, studied them, learned them, and came away saying, wow, this all makes sense. Relativity made sense. Quantum mechanics made sense. Jump to, I don't know how many years later, I've retired, moved to New Zealand, and I'm beginning to notice that wherever I look, movies, articles, newspapers, magazines, quantum field theory isn't being mentioned. Everybody's talking quantum mechanics and the paradoxes of relativity, the things that I call Einstein's Enigmas. And I said, well, I'm a guy, I guess I was looking for a retirement. Everybody wants a retirement project. That became my project. I want to tell you, in selling this book, I'm not making money from the project. I'm putting money into it. I put effort into it and money because it's become my mission to help, and I'm not the only one doing this, to help tell the world at large, fields is the answer, quantum fields. Now, I don't know how many, yes, I want to say, by the way, if anybody has questions, please do interrupt. Yes?
I told you I was a moron. I don't know what quantum field means.
You will after this talk. She doesn't know what quantum fields means. I hope you will after this talk.
I thought I was supposed to know that to start.
Yeah, no. Okay. But if you do have questions, I'd rather have you with me than go on without you. So that's the story, really. So I wrote the book in New Zealand. I found out some recent events, and I did a second edition. And I think it's a very unique book in presenting in a very understandable way, without any math, how quantum field theory makes sense. Now, I don't know how many of you, I think the fact that you're here shows you have an interest in physics. Have any of you previously made any attempts or read anything about physics that's maybe confused you, or maybe it didn't, or are you all here? So how many people here, raise your hand if you've previously tried to read or learn something about physics? Ah, good. Okay, well, I hope you will all see that what I'm saying is true. Okay. Oh, okay. Yeah, you told me that, right, yeah. Okay. So I'm now, I want to add one more to this. I told you I think an intellectual tragedy has happened, that the world is drowning in confusion over physics when they don't need to. There's also a personal tragedy that hits me very hard because I studied with Schwinger and I appreciated his brilliance as other people did, and he's forgotten. Of the people here, and a lot of you have looked into physics, how many have heard the name Schwinger? Raise your hand. 3.5. At Georgetown University, I gave a talk to the physics department. I asked the same question. 3 people raised their hand. The forgotten man, the forgotten genius, and if that's not a tragedy, I don't know what is. Okay, now I'm going to try to explain to you at a very superficial, quick level what quantum field theory is and how it resolves Einstein's enigmas. So the first question we have to look at is, what is a field? Well, I'm going to give you a quick answer, The quick answer, a field is a property of space, a condition or a property of space. That's what it is. But it's not an easy concept. As a student, I didn't grasp it right away. I think it was about a year before I got comfortable with the idea of fields. And you will see in my talk that the physics community also took a long time to get comfortable with the idea of fields. All I can hope to do is give you a little glimmer of what it means that space has properties. To help do that, I'm going to use a color analogy, which is the only thing that I have introduced in my book. My book is, of course, nothing that I have done. It's an attempt to tell people about the field theory that I learned from Schwinger. But I did introduce the idea of colors, which I think is very helpful. And properties of space are we can all picture objects. We know what objects look like. But to picture space with properties is hard. But we all know how objects have color. Color doesn't exist by itself. There's no such thing as color alone. But wherever you look, you see everything has color to it. The sky is blue. And if you can picture the sky being blue, maybe you can picture space having colors. And you're going to see there are 6 of them. And they all exist in space. And each one represents a field. Okay, I'm now going to I'm going to illustrate fields by telling you about the 6 fields of physics and how they came to be recognized as fields. The first field that I'm going to talk about is gravity. It's the oldest theory in physics. It was developed by Newton in 1666. He had fled London because of the Great Plague. He went to his mother's farm, where, as we all know, he was out in the field and he saw an apple fall from a tree. It's a true story. And wondered if maybe the force that was pulling the apple to the earth could be the same force that held the moon in its orbit, because that was a big mystery of the day. Astronomy had been developed by 1666. They had telescopes. Galileo had learned how objects, work and how they fall at the same. He had done experiments with falling objects, but nobody could explain why the orbits of the moon around the Earth or the orbits of the planets around the sun. And Newton wondered if the same force could do both. Make the apple fall, hold the moon in its orbit. And he had the brilliance and the mathematical ability. He had to invent calculus to answer the question. It took a long time to get the data right and to get the facts right, but he came out with a theory, a simple law of gravitation that explains why an apple falls and why the moon, and when he predicted, by the way, when he predicted the length of the lunar month, which is something like 28 or 29 days, he almost had a heart attack. The excitement of seeing this number come out right. But what I think is most remarkable about Newton is what I put up here in this slide. He not only developed this theory, the first great breakthrough for which he received universal acclaim, he also recognized that something was missing, that one body may act upon another at a distance through a vacuum without the mediation of anything else is to me so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. If that's not a cry to have a field in between, I don't know what is, but the fact is that for 2 centuries afterward, everybody believed this absurdity, that yes, objects, and even recently Richard Feynman propagated the same idea. There are no fields. One body acts on another body without anything in between. Newton had the intuition to tell him that that wasn't right, and he had also the ability mathematically to work out the theory that he did. But let's now pass from Newton to comment to the person who actually did, I think it's that one there. No, I guess not. This one. There we go. The person who supplied the field. In 1915, over 200 years after Newton, Einstein finally in 1915 developed equations that described the gravitational field. And I'll let him tell you in his words how he sees the gravity working. The Earth produces in its surroundings a gravitational field. That's what acts on a stone or an apple or the moon and produces the motion, the fall. There are laws, and the thing, and I forgot to say when I talked about fields, that what you have to have in physics, you just can't have a concept, an idea. You have to have equations that go with it from which you can calculate things and see if it checks with experiment. And the equations that go with fields, with quantum fields, are called partial differential equations. Don't worry about it. I won't tell you what they are, but they describe the field intensity at every point in space and how it is influenced by other fields and how it propagates and evolves and changes with time. And Einstein developed those equations for the gravitational field. And here's the picture that came out of all of this. And here I'm using the color analogy. The color blue I've chosen to indicate the gravitational field. And I believe that everybody here is fairly comfortable with this concept. The space around the Earth has an attractive property there. It has a field. So it's not quite tangible. You can't touch it, but there's a property of space that causes objects to be attracted to the Earth. Now I'd like to take you to the next field I'm going to tell you about, which is the electromagnetic field, which was actually recognized as a field before gravity. And I'll tell you quickly, the first person, and this is really very significant, Michael Faraday, in 1845, was doing experiments with magnetism, and the bottom picture shows an experiment that maybe some of you even did in school, where you put a piece of paper over a bar magnet and you sprinkle iron filings. You've done it, huh? And you see they form a pattern. Well, I'm going to comment now, make one of my own comments, and being kind of familiar with a lot of physicists, I think what a lot of physicists don't have is intuition. They can do the math, but they don't have the intuition for reality. Faraday had it. In fact, Faraday was no good at math. He was the worst mathematician of any physicist. But he had the intuition. He said, there has to be something there. And let's call it a field. And I, myself, in London, visited the museum where the book, his lab manual, his lab notebook that contains the word field, written in 1845 for the first time. Once again, I'd like to turn to Einstein to comment on this. And I won't read this to you. It's just basically saying, you can read it, it's basically saying in Einstein's words, and remember, he was the one who gave gravity its field status, and he's looking back on magnetism, and he's paying tribute to Faraday, who could see we're not content to mean that the magnet acts directly on the iron through the intermediate empty space, just as Newton couldn't accept such a thought. There must be a magnetic field. Oh, wrong button. Okay, so I'm now going to illustrate the two fields that I've talked to you about. I've given the color green, and again, these colors, of course, are imaginary and arbitrary. It's just an aid to help you visualize that there are properties out there in that space that we ordinarily think of as being empty. It's not empty, it's filled with fields. This is supposed to be a nucleus, an atomic nucleus, positively charged, so it sets up an electric field around it, and that's what this greenness indicates. Here's this picture of the Earth that I showed you before, but this time I've added onto it a green halo on top of the blue gravitational field. This represents the magnetic field of the Earth. And it's green because I've assigned green to electromagnetic fields. And it doesn't replace the blue field, it's on top of it, they're both there. And it doesn't go to zero, it continues just as the blue field. These fields don't cut off, they extend through all of space. Okay, there are two more fields that I'm going to pass over very quickly. They're nuclear fields. They exist only in the nucleus of the atom. They're called the strong field and the weak field. The strong field holds the nucleus together, stops the protons from repelling each other and flying apart. It's a very short-range force. It doesn't go very far, but it falls off quickly, very quickly. And I've tried to indicate its presence by taking that picture of the nucleus that I showed you before with a green electric field and superimposing on it a little purple, because I'm using the color purple for the strong field. I'm not showing it inside the nucleus, but it's inside the nucleus where it's really doing its work, but it extends outward just a little distance. And that's just a picture of the strong field. And there's also a weak field that I won't go into at all that exists inside the nucleus. It's even shorter range than the strong field, and it's what causes decay, radioactive decay. In other words, it kind of makes the nucleus disintegrate. The last, oh, something went wrong here. That should say the matter fields. The last two fields I'm going to tell you about, and remember, we're doing this very superficially. You know, I don't want to bore you completely because I don't expect anybody's going to come away and say, oh, I understand what these fields are. I'm trying to give you a superficial picture of what they're like. And here I'm quoting another Nobel laureate, a recent one, who actually played a key role in giving the weak field its status as a field, Steven Weinberg. Just as there is an electromagnetic field, so there is also an electron field. The electrons, you know, are the things that we think of as particles that go in orbits around the atom or that move through the antennas to give off electromagnetic radiation. They're not, in quantum field theory, even the electrons and the protons and the neutrons are not particles. They're tiny, they're fields. It's an electron field. They're found in the bundles we call electrons, and likewise for every species of elementary particle. But these bundles are not little round balls. They're blobs of field that extend out. The basic ingredients of nature are fields. Particles are derivative phenomena. Reminds me of my friend Art Hobson's paper. I think I told you that there are other people recently who are also trying to spread this gospel about quantum field theory, and Art Hobson is one of them. And he recently published an article with a similar title. There are no particles, there are only fields, published in American Journal of Physics. So there is, I believe there is hope that this cause will eventually succeed. Although when a lie, and it is a lie, well, no, I shouldn't say it's a lie, it's a choice. When a bad choice has 75 years of momentum behind it, 100 years really, it's very hard to stop it. So I'm telling you about the two matter fields. But to understand the matter fields better, first I would like to illustrate what a matter field looks like by taking you inside the atom. Probably most of you, certainly those of you who have looked into physics before, have seen this picture of the atom. Ernest Rutherford, developed this picture, I think it was 1911, after some experiments that were brilliant experiments. And it was called the Rutherford atom. And there you see the nucleus with its little balls of protons and neutrons. And here you see these other little balls of electrons in orbit, like planets around the sun. That's the old picture. That's the classical picture. In quantum field theory, this is what the atom looks like. Instead of a nucleus made up of little balls, and I'm using my color analogy now, I'm using red for the nuclear fields and yellow for the electron and fields, because there are two kinds of matter. I forgot to mention this. There's the heavier, call them particles, like the proton and the neutron. They're called baryons, which means heavy. And there's the lighter particles, like the electron and the mu meson and neutrino. They're called leptons, which means light. And I've assigned arbitrarily the color yellow to the electron and red to the baryons. So here you see a blob of red in the middle, representing the fields of the nuclear particles. And here you see a yellowness of space, just like the green electric field that's out there too. And I didn't show the green field now because I want you to focus on the yellow part of it. They're together. This is what the electron looks like in quantum field theory. Well, not really. I've oversimplified it. It's much more complicated than just a spherically symmetric scheme of yellow. It's more complicated, but the idea is that it's a yellowness of space, it's properties of space, not particles. And I guess if I were to pick maybe one picture from this talk to convey the essence, maybe it would be this picture. This is a difference between quantum mechanics, which sees everything as particles, and which rules the roost. 90%, 99% of what you read is about quantum mechanics, and quantum field theory. Now, I don't know how much, I have to at least mention this. I kind of left something out when I told you about fields. It was true, but I didn't tell you there's something kind of special and unique about quantum fields. And I'm going to just touch on this, take a little bit of the historical approach, and tell you how this came about. Quantum fields, the special thing about them is that they exist in discrete units. They're called quanta. These discrete units are called quanta. This was discovered by Max Planck the year 1900, and I can't find anything more symbolic and more symbolism than the fact that this great change, this introduction of the quantum, was made in the centennial year. He was working, trying to understand the electromagnetic radiation given off by a hot object, like filament in a light bulb, or the sun, or a heater in your house gives off electromagnetic radiation. And the data didn't make any sense. It didn't jibe with Maxwell's theory. This was quite a problem at the time. And he somehow found out, trial and error, I don't know, found out that if he introduced an assumption that the radiation that was being emitted from a hot object was not emitted continuously, but consisted of discrete units, this much here, this much there, this much, all superimposing, but each one having its own identity, that would explain the equation. He also was very excited. He told his son that day, "Today I've made a discovery as important as that of Newton." And indeed it was, because it led to quantum mechanics and quantum field theory. I'm just talking about the light being emitted from a hot object, and the recognition by Planck that it must be emitted in units. And he called them quanta, which is a plural of quantum, and quantum means so much. And in my book, I illustrate this with the analogy, with a sugar analogy. I say, suppose you have 2 bowls of sugar, and one bowl contains granulated sugar, and the other contains sugar cubes. Do they still use, are there still sugar cubes used? I haven't seen them. Okay. I remember in the old days, I remember grandmother would put a sugar cube in her mouth and drink the tea through it. Okay. So if you have 2 bowls of sugar, if it's the one here, you can take as much or as little as you want. You can take the tiniest amount, a half teaspoonful, whatever. If it's the other one, you can only take 1 lump, or 2 lumps, or 3 lumps. That's sort of the difference between the classical field concept and the quantum field concept. In quantum fields, the fields are not lumps, they're not cubes, they're spread out in space, but each unit is distinct from the others, and each unit lives and dies as a unit. If it's absorbed, as I thought you were going in the direction of absorption, but that was not the case. If it's absorbed, say in a photon from the sun travels, or from a lamp travels and hits your eye and is absorbed in an atom of your eye, all the energy of that photon collapses into that single atom in your eye. The field disappears. This is the toughest concept in quantum field theory. I mean, if you can handle the concept of fields, you're doing great. If you can appreciate the idea of quantum fields, you're a genius. But, she's had practice. That's my wife. But the idea of field collapse is kind of mind-boggling, that this unit of field, spread out as it may be in space, suddenly, instantaneously collapses into a single atom. And yet, as I said in my discussions with physicists who have a tough time with it, there's nothing inconsistent about it. It may not be what we expect. It may be contrary to our intuition. But listen, our intuition tells us the Earth is flat. We got comfortable with the idea that it's round, you know? So we can live with it. There's no paradox involved there. It's just not what we expected. So I've told you about the basic quantum idea, and I've told you about field collapse. Let me see what's next. Oh yeah, so I want to sum up here, and then I want to go on to Einstein's Enigmas. How am I doing here? Well, I better hurry up, because I still have Einstein's Enigmas to tell you about. So let's just say quickly, this is a summary from my book of a table showing the 6 fields of physics. There's a little footnote about quarks and gluons, which came along more recently. The funny thing is, you don't see them. They make up the strong force field, and they make up the baryon field, but they're invisible in themselves, so you don't have to worry about them. The fields all have quanta associated with them. They all have different ways of interacting with other fields, and I've assigned an arbitrary color to each of them just to help you visualize them. Okay, Einstein's Enigmas. There are 3 of them. Once again, I hope I won't be quite as superficial here. If too many people go to sleep, I'll move more quickly. There are 3 Einstein's Enigmas. Special relativity that he developed in 1905, general relativity, which is the theory of gravity that he developed in 1915, and quantum mechanics that he started going in 1905 with a paper that won him the Nobel Prize, actually, but he kind of abandoned the ship. But he did, I call him the grandfather of quantum mechanics. So I say that I might have made a mistake. He started quantum mechanics going with his 1905 paper, and that's the one with the paradoxes. So Einstein's Enigmas are special relativity, general relativity, and quantum mechanics. Okay, in each case, I'm going to try to convince you that there are paradoxes, and people cope and struggle trying to understand these, and they give up. I've put in a couple of my favorite quotes from my book. If Marilyn Vos-Savant, who's supposedly the smartest person in the world, can't understand relativity, I mean, right there, I rest my case. In New Zealand, I think I forgot to tell you that this mission, or maybe I did, I think I mentioned I had moved to New Zealand, and that's when I started my book project. So my wife and I enjoyed New Zealand very much, and we love the people there. And one of the columnists there writes a kind of humor column. This is the thing I misquoted to you before. you were actually, oh, you said you were a moron when it came to physics. Well, he says a while back I bought an idiot's guide to relativity, from which I learned only that I hadn't yet attained the rank of idiot. I mean, nobody can understand this. So I'm just going to single out one paradox to spend just a little time on, and I hope you try to follow this. One of the paradoxes of special relativity is that time slows down when you're moving. This follows from Einstein's principle of relativity, but it doesn't make any sense. And it leads to this picture that you see here. The space traveler shakes hands with his twin here. He takes off in his rocket ship, travels for many years at almost the speed of light, and he comes back 50 years later, and his twin is an old man, and he's still almost the same age. How can that be? Quantum field theory provides the answer. And this is going to be the toughest thing for you to follow here. I decided to spend a little time on this, but this is one of the insights that I had in graduate school, how quantum field theory explains so much. And I think many of you can follow this. Consider two people in a raft. Now, the reason I'm taking this analogy of people communicating with each other is because in quantum field theory, everything is made of fields. The rocket ship is made of fields, the instruments are made of fields, the people are made of fields, their brains are made of fields. Everything slows down because they're moving. Why does it do that? Well, consider the analogy of two people communicating on a raft. And one person calls to another person, A calls to B, and when B gets the message, something happens. It's sort of like fields. This is the analogy of fields communicating in a person's brain or in an instrument, in a clock or anything. Things are not static. Different parts of an object are always communicating with another. Things are happening because of these communications. Fields don't propagate instantaneously. They take time. There's field equations that govern them, and there's a constant called c that says just how fast a change can propagate. So, back to the raft. A calls to B and makes something happen. Now, if the raft is stationary, it'll take a certain time for the sound to get from A to B. If the raft is moving, B will have moved to this point here, and the sound will take a little longer because it has to travel a greater distance. In fact, if the raft is moving very fast, B may be way down there, and the sound may take a very long time to get there. Something that B is supposed to do won't happen until later. And even if the raft is in the same direction, longitudinal to the motion, the same thing. If A calls to B and the raft is moving, B will have moved to a different position. And it'll take longer for the sound to get there. Okay, to me, this is very clear, obviously. But this is an insight that I think everybody who has an interest in physics can understand. And I think you can see that if everything is made of fields and things happen because a field here has to propagate a change to a field there, it'll take longer if it's moving. That explains this twin paradox. It explains why things happen more slowly. And they say time slows down. Time doesn't slow down. Time is just a measure of how things change. Things happen, everything happens more slowly if it's in motion because everything is made of fields and it takes time for fields to propagate from here to there. This is a summary, which I think I'm going to skip over, of 5 paradoxical results of Einstein's theory of relativity that all make sense, are perfectly understandable when you realize that things are made of fields. I call this the bottom-up approach. You see, Einstein took the top-down approach. He said there's a principle of relativity that says that the physical laws must all be the same regardless of your state of motion, and from that he deduces all of these effects. That's what is taught today in all the schools. Most physicists, not only most, I would say just about all, start with it. But the bottom-up method provides insight into why these strange things happen. The word quantum is used all over the place for many different things. I told you where it came from and its original meaning. In quantum field theory, the word quantum means a unit of field, an excitation in the underlying field. It has a certain energy, it gets created, it can disappear and collapse, as I've told you. That's the only meaning of the word quantum that I'm talking to you about. Yes, it's you. I mean, quantum mechanics itself, people could bring up all sorts of questions about quantum mechanics. I'm not here to try to answer those. I'm here to tell you about a theory that makes sense. So, general relativity, a few more quotes to show you that even Einstein's daughter, the first president of Israel, he was on a transatlantic trip with Einstein, crossing the Atlantic Ocean, and when he got to America, he said, Einstein explained his theory to me every day. And on my arrival, I was fully convinced that he understood it. I didn't put it up, but Einstein's wife, unlike my wife, who understands quantum field theory, asked Einstein, was asked by a reporter, did she understand relativity? She said, understanding relativity is not necessary for my happiness. So the answer, the curvature of space-time that you may have encountered, that's the paradox of general relativity, is answered, and here I'm quoting Frank Wilczek, a Nobel laureate who is also an advocate of quantum field theory and has written a book called The Lightness of Being. It's written at a higher level than mine, but I recommend it if you're up to it. Describes general relativity and points out, as other people have, that it can be looked at two ways: curved space-time or a metric field, that is a field in space. And as he says, the field view makes Einstein's theory of... Now, by the way, Einstein himself kind of bought into the curvature of space-time, and he liked that concept. He didn't like it initially. It was Minkowski who came along with this four-dimensional stuff and the geometrical analogy. But the equations can be taken just as field equations. He says this makes it look more like the other successful theories of fundamental physics, the other fields, and makes it easier to work toward a fully integrated, unified description of all the laws. As you can probably tell, I'm a field man. So there are a few people around who are trying to spread the word about fields. The third enigma, Einstein's Enigmas, is quantum mechanics, and this is quite, there are many, I could have quoted Richard Feynman. How many have heard of Richard Feynman? Sure, almost everybody. And he's the devil in the story. Schwinger is the hero, Feynman is the devil. Feynman said, leave your common sense at the door if you want to try to learn about what happens in quantum mechanics in the atom. I love this story here about a young theorist who, quite promising as a graduate student, then dropped out of sight. I asked Phil what had interfered with his research. Phil shook his head sadly and said he tried to understand quantum mechanics. I mean, physicists don't understand quantum mechanics. How can the public? And in the meantime, under their very noses, so to speak, is sitting this beautiful theory. The third, I'm going to show you three of the major paradoxes of quantum mechanics, and I'm going to go through them very quickly because I don't want to go an hour and a half. I want to finish easily within an hour, and I want to allow time for questions afterward. So there's wave-particle duality. Oh, I do have to tell you this. I mean, this to me is so poignant. This is another personal tragedy here. Einstein started quantum mechanics going with his 1905 paper, What is the Photon? And he introduced the idea there had been 100 years, no, excuse me, not 100 years, well, since Maxwell, and say 50 years, of belief in fields, in the electromagnetic field. But Planck had come along in 1900 and said, well, the electromagnetic field is quantized. It's broken up into units. And Einstein came along in 1905 and said, not only is it emitted in units, it's also absorbed in units. It must be a particle. But poor Einstein was he saw the paradox here. And Einstein did have physical intuition, unlike so many others, and he couldn't accept this. There's two interpretations that conflict with each other. And if this doesn't break your heart, what does? Shortly before his death, all these 50 years of pondering have not brought me any closer to answering the question, what are light quanta? I'll tell you the story of what might have happened, and things would have turned out much differently in a moment. But the wave-particle duality is a big bugbear about quantum mechanics. Physicists make the joke, light is waves on Mondays, Wednesdays, and Fridays. It is particles on Tuesdays, Thursdays, and Saturdays. And on Sunday, we think about it. The second paradox in quantum mechanics is the uncertainty principle. In a nutshell, in quantum mechanics, you have particles, and the particle might be here, or maybe it's there, or maybe it's there. Who knows where the particle is? Find the particle, here. In quantum field theory, the particle is a field. I showed you a picture of the atom with the electron field. It is here and there because it's a field. It's not a particle. Then there's the role of the observer in the famous Schrödinger-Cat experiment, which Schrödinger proposed to show the absurdity of believing in such nonsense, and people have taken it the wrong way. They say, oh, the cat is in the superposition of being alive or dead at the same time until somebody looks. In quantum field theory, that just isn't true. And I think I have a summary here. Yeah, explanation. Wave-particle duality, there are no particles, there are only fields. Uncertainty principle, fields are not localized, they spread out. No role of the observer, fields collapse suddenly. That part of it is not explained by quantum field theory. We do not have a theory for field collapse. But hey, we don't have theory, there are lots of things that we don't have theories for yet. But it occurs, and there's nothing, we accept it, we have to accept it, there's evidence for it. So I just want to say, before I do my final bit, that there is hope in the future. That even though there's 100 years of momentum behind quantum mechanics and the top-down approach to special relativity and the geometric interpretation of general relativity, that things may change and quantum field theory may have a renaissance. Frank Wilczek and Steven Weinberg and others I could mention, Frank Wilczek is certainly one of the key players. He got the Nobel Prize for what he did in working out the Standard Model. In fact, if I have time, I want to tell you about, no, I guess I don't. But I want to tell you this. Richard Feynman, I didn't go into this history, but there were three key battles. I call them three rounds in the battle between particles and fields. And the third one occurred in around 1948 when Schwinger and Feynman and Tominaga shared the Nobel Prize. And Schwinger's field approach lost in the physics community, and Feynman's approach of Feynman diagrams involving particles won. And everybody uses Feynman diagrams with particles. In Wilczek's book, The Lightness of Being, he tells how he met Feynman. And this is another little personal vignette that I think is heartbreaking. Feynman told me that when he realized that his theory of photons and electrons is mathematically equivalent to the usual theory, actually not usual, meaning field theory, it crushed his deepest hopes. He gave up when he found the fields, introduced for convenience, taking on a life of their own. He lost confidence in his program of emptying space. See, all through most of his life, Feynman said there are no fields, there's just particles. And he says this to Wilczek. I don't know just what the year was, I forgot. And nobody knows this. It's another what-if kind of things. During his search for a unified field theory, Einstein rejected quantum field theory. He had asked a friend, his name was Valentin Bargmann, to give him a private tutorial on the subject. It's not surprising that he rejected it. At the time, quantum field theory, this was in the late 30s, I believe, or possibly early 40s. Of course, Einstein was in this country by this time. At that time, quantum field theory had not been perfected by Schwinger, and it was not successful. This wonderful Nobel Prize-winning event of 1948 had not yet happened. And Bargmann certainly was not a spokesman. What did he know about it? So I say in the book, and this is me speaking, I can't help but wonder what might have happened if Einstein had waited a bit longer for his tutorial and chosen a different tutor, perhaps Julian Schwinger. The year is 1954. The 36-year-old Schwinger, who had just completed his monumental papers in the theory of quantized fields, comes to Princeton to meet the 75-year-old Einstein, who is to die the next year. Professor Einstein, he begins, I want to show you a theory that unites all the known forces, as well as matter, into a field theory that incorporates the principle of relativity, as you have formulated it, and the quantum principle that you helped introduce. It is a theory that is philosophically satisfying and has produced agreement with experiment to an undreamed of precision. That's what happened in 48. Well, go ahead then, says Einstein, and Schwinger proceeds to expound his theory in Einstein's Princeton study. The sessions last many weeks. Finally, Einstein says, this is indeed a beautiful theory, but it seems there are 6 separate fields. As you know, and some of you have read about Einstein's later years, you know about his quest for a unified field theory. As you know, my hope was to find a single field that comprises all forces and matter. This theory of yours does not meet that objective. True, says Schwinger, but may I remind you what your friend Pauli once said to you, what God hath put asunder, let no man join together. If the God you often refer to chose to have 6 fields, it is not for us to second-guess him. Pauli also said to you, it is not for us to tell God what to do. All right, says Einstein, I can accept the 6 fields, but there's a further problem that is more troubling to me, the probabilistic nature of your theory. I have never been able to believe that God would play dice with the world. And you've probably heard Einstein's quote about that. I understand, says Schwinger, and I admit that quantum field theory has not solved the causality problem, but at least it has localized the probability aspect to a single event called field collapse, an event that is not covered by quantum field theory. Quantum field theory itself is causal. Causal meaning determinate, no guessing. But it only takes us so far. At some point, a discontinuous event takes place that is not covered by the theory. This does not invalidate the theory. It is possible that at some time a theory will be developed for field collapse, and it may turn out to be causal after all. On the other hand, it may be that it is truly probabilistic, and perhaps God does play dice with the world. Either way, it doesn't detract from what quantum field theory has accomplished. And what quantum field theory has accomplished is explain virtually every observation that we have made, and to provide a picture of nature that makes sense. Einstein gives in. This is back to my fictitious account. He is captivated by Schwinger's elegance and the soundness. By the way, Schwinger, having heard him lecture for 3 years, unbelievable, elegant, brilliant. And the soundness, both conceptual and mathematical, of his theory. He recognized that quantum field theory does meet his desire. It is a field theory without putting together what God hath torn asunder. He then announces to the world that quantum field theory is the theory he has been looking for all his life. Of course, this turns the tide and quantum field theory becomes accepted throughout the physics and the public communities, restoring the popular appreciation and understanding and glory in science that once existed in the times of Newton and Maxwell. But that didn't happen. And that's why I'm here.